Thank you all for being here. So before starting my talk, which will be based on enhancing airline forecasting machine learning, let me just tell you a little bit about myself. So I'm from TU Delft. I'm an aerospace engineer. I don't have a background in computer science. I don't think that's needed to learn about machine learning. There's so many sources of information nowadays. But I first got comfortable with how good machine learning, what the potential to it is during my PhD. I work with reinforcement learning for ATC safety. I think some of the talks today will talk about reinforcement learning. Very impressive tool, cannot emphasize it enough. But now I focus more on airline planning and scheduling. And the focus on this planning and management is always trying to predict the future, right? Predicting what's going to happen so airlines can make better decisions. And for that, we use machine learning a lot, more specifically supervised learning. So let's look at the problem that we have nowadays. I took this information from an aero control document. So at the beginning of this year, they say average departure delay, almost 14 minutes per flight. Reactionary delays, so delays that progress over legs of a flight, almost 7 minutes average delay per flight. Airlines, whom I now work more, they contribute almost 4 minutes to the average delay. Now, airlines, let me tell you, they don't want to be delayed, right? But things happen, and sometimes they cannot, well, better plan. But for airlines, passenger connection time is essential, often the most crucial element in their operations. Imagine, for example, a hub-and-spoke airline. Swiss Airlines, for example, is a perfect example. They have a hub at Zurich. They might have a flight from airport C to the hub, and then a flight from the hub to D. So they might then take a passenger from C to D through their hub. Here, passenger time is crucial, because if the first flight is delayed, their passenger is going to lose the connection to airport D. This means the airlines are going to have to compensate this passenger, right? So nobody wants a situation to actually predicting these delays and telling an airline which flights are more risky and where you should focus your resources are essential. So when approached by airlines, this is what we told them. We have a research hypothesis, which is supervised learning by looking at historical data. With that, we can better predict future events. In this particular example, I used the use case of predicting future departure delays. But so we're making the case where if you can better predict these delays, you can better plan your flights throughout the day, so you will reduce your costs, and hopefully will also have a less environmental impact. Why is this? Often airlines are more fuel. They're hoping that by the end of the day, they have a lot of delay. They maybe are able to go faster. There's a lot of expenses in the fuel, so we're also trying to decrease the amount of fuel that airlines use. Well, this is simpler said than done, because often, well, we have many issues when trying to build these models. Supervised learning methods need a lot of data to be able to correctly predict the future. Well, we work normally from a single perspective, of a single airline or a single airport. And airspace is full of agents working together, so multiple airports, multiple airlines, weather, ATC, all of these agents contribute to these final delays. If we're looking only from one airline, there's a lot of data that we're not seeing. So there's a lot of information that we don't have available. So there's a lot of randomness that we consider in our models. Randomness is just to be sort of not knowing enough about other airlines, other airports. Also, in most of the data that you get just before the flight, you can trust it. You can say 15 minutes before departure, you can say you have pretty good time on how much the delay will be. Airlines want this information at the beginning of the day, most of the times, right? They need this information in advance to know where to put their resources, to know which flights to focus. So, well, but at the beginning of the day, the information that you have is not very accurate. Another thing, imagine a dispatcher, the airline that has worked 20 years with the same model. Now you go to them and say, we have this machine learning method that you can use. And they're going to say, OK, explain how it works. We're going to say, well, a lot of times you don't really know how it works. They're going to say, well, no, thank you. I'm going to keep using the same model. I've been using it for 20 years with some success. Right, I'm going to focus on this particular use case that we did. So we worked with Airline. I cannot say the airline's name. Again, they're very careful with their data. But we tried to estimate their departure delay. So this is some of the elements that we found to be what the model found to be the most important. This shouldn't be of any surprise. So what are the important elements? So previous flight, previous leg, how delayed it is, right? Makes perfect sense. If it's delayed to the hub airport, it's going to be quite delayed on the departure for the next flight. Then current ISAT delay, how heavy is in terms of passenger the aircraft is, more passengers, more time to board. Current delay airport, this is very important. This is already the first more important element. Our airline only had this information for the hub airport. Again, very limited data. But this is quite important, meaning for other airports, our module is not so good because we just don't have that information. Then average delay, that normally we have historical data in this flight. Passengers that need wheelchair, this delays boarding, again, time of month, so how busy the airport is, how busy flights are. So none of these elements are a surprise to you, right? All of these you can understand how it contributes to delay. The issue here is much of this data is actually confidential to airlines, right? So airlines know more or less how delayed their flights are. They know how many passengers they have. We're not going to get this information from our airlines. So data accuracy varies over time. For example, delay previous flight, the most important element. At the beginning of the day, you don't know how late the third leg is going to be. You can try to predict it with some degree of success. Finally, additional airport data is missing. So this airline in particular, it had information of how busy the airport was, the hub airport. It doesn't have this information from other airports, right? And also this is an idea of an estimation. We don't know what the airport is doing in terms of the other airlines, right? So I told you some values that make sense, but I also told you there's a lot that we're missing. So when you look at the results, so I told you there's an average 14 minutes departure delay. So we actually run different models at different points in time. Why is this? Because at different points in time, you have different accuracy. So at different points in time, actually each model decided in a little bit of a different feature importance because it decided there's some values it cannot really trust. So the model can give us an indication of how trustworthy this data is. But so 1 hour and a half before departure, we got 8.5 minutes of delay in terms of medium absolute error. And minus 15 minutes before departure, we put it down to 7.5. So I told you there's 14 minutes delay average in January 2014, and we have an accuracy of 7 minutes and a half. Not bad, actually it's comparable to existing research, not perfect. Why? Lack of data, lack of the full picture. But what the airline wanted these numbers is to know, again, where's the risk? Where should we focus our resources so we make sure that we guarantee a safe connection time for our passengers? So we give them an idea of distributing the results of our model. So we don't give them only a value, we give a distribution. And we see that 1 hour and a half in advance, our model tends to have a big variance. So it says, okay, I'm going to give you a delay, but I'm not very sure. And this lack of certainty is because, well, the data that you have is not very accurate. And then we see minus 15 minutes to departure is more certain. This is most of the cases that we see. Of course, there's exceptions, but most of the cases that we see is that the model cannot be very certain 1 hour and a half in advance. There's lack of accuracy, but then it becomes quite good before departure. Of course, 1 hour in advance is what the airline is looking for. So this is something. They like this. They like this kind of variance. They want to know where the problems lay. They also want more. And then our response typically is, well, we need more data that you don't have. So this is a problem. I'm going back to the other problem that I mentioned, which is how to convince them to use this, right? People that work at airlines, they're very good. They have a lot of knowledge. Their head has so much information. A lot of times they're as good as our models, so we have to justify why they should use them. So there was a EASA concept paper, the first attempt at defining what would be necessary for certification. They say explainability is a key element. If you cannot explain it, you cannot certify it. If you cannot certify it, people are not going to use it. How do we explain something that is quite complex? A lot of times the result is, this mix of this pattern between variables. What we came up with, and so far we've had some good reactions, was dispatchers are shown this visual interface where we say, for this flight, for this airport, we have this predicted delay. And they might say, if it matches what they're expecting, they don't ask any more questions. If it doesn't, they're going to say, why? If it's much lower or higher than what they're expecting. So then we looked at the features that were more important, together with which features from those that are more important tend to be different from the average. And then we say, these features that we found to be very important, they now have a value that is very different from the average, right? And that we see that it's working. We also give them information of when this model was a prediction moment and the variance. So we give them an idea of risk and why their risk is. So, and this is what we've achieved so far in terms of good results that this airline can trust our methods. Very initial situation, but what we want, and actually what I'd like to hear today is, how do you make it more explainable, right? How do you convince people to actually use this if you cannot even, we don't even know how to certify it yet? Yeah, thank you.
Thank you very much. Very interesting. I really like the aspects of the explainability, and it can start a very big and nice discussion.
Very big, yes.
Different ones. Questions? There it is.
Thank you. Thank you very much for your presentation. Having worked a little bit in the airline industry, I have some question regarding how you took into account the business rules that Pavel was talking about just before for your model, because I know that for multiple airlines there is a lot of business knowledge that sometimes isn't present in the data that you should include and take into account. So how did you manage to do that?
Excellent question. You know, what I feel these models, most of them, they're just predicting what the airline is going to do, right? Because inherently to the delay, historical delay includes the decisions that the airline took. Meaning, the airlines at some points decided to prioritize some flights, meaning they reduced the delays of those flights. So the model, when it looks at historical data, it doesn't know those business rules, but it knows that that flight somehow had lesser delay. And that's because business rules are intrinsically there. Second part was, I didn't put that here because, to be honest, we have to be a bit careful with the information, and this hasn't been published yet, this paper. But also another element that's also very important was number of passengers in this program, in the airline program, membership program. Because the models show that the airline puts more resources in flights with more passengers in its membership program, also connected with a smaller connection time. So what the model is learning is that the airline tends to put more resources into flights where there's more important passengers, right? It cannot tell exactly how, but it can tell that it does. There's also a problem, right? Because if you tell an airline, okay, this flight here, based on historical data, only is probably going to have this delay. But what if they say, oh, the risk is not so much, you don't do anything. But what if that delay is because in the past they put resources into their flight, and so that's why the delay was lower? That's a thing with these methods, right? They learn some intrinsic pattern that may not be explicit to the input data. I hope this answered your question. So my answer is there's a lot of information there that we don't have, but it's there inherently to some aspect.
Hello, Marta.
Hi.
Thank you for the presentation. Well, I have a lot of questions and comments, but the most important is, and we can keep in this slide, is why are you using the delay of the previous flight and not the available turnaround time? Because if you have 3 hours of scheduled turnaround time and the previous flight is delayed 1 hour, you don't care. The important thing is the time that the airline has to unload the aircraft and prepare it for the next flight. No?
Actually, when we started doing, I completely agree with you. When we started doing, we used the turnaround time, but then the model just didn't select it as one of the important features.
One of the less important.
One of the less important, yes.
Which model are you using?
I use random forest, but I think that information...
Try GVDTs.
Sorry?
Try GVDTs.
Okay, fair, I will. So I'm guessing maybe that information is already there somehow? That's what I'm guessing. But I agree, it would make sense to have it. But so when we made this, and this was the most important element. So I think the model is somehow just getting that information from other elements.
The order makes sense to me. Yeah. I was only wondering why to use this and not the available turnaround time, because then they are giving you more or less the same information.
That's what I think,
but
yes.
The second one is more precise. No?
Agreed.
Because here, for the cases where you have very tight turnaround time, this one is going to work. But for cases where the turnaround time is 3 hours, this is not going to work.
Completely agree. So I'm thinking maybe it's the specific flights that we looked into, the specific airline that the model decided to take information from the delayed previous flight. Just to work, but I think information is there, but it's hidden. Probably when you look at the other airlines, other airports, there's not going to work as well.
Thank you very much.
No problem.
Thank you very much.
Thank you.